Hey now, everyone. Welcome to another episode of the Microsoft Networking Academy. I'm your host, Jamie Schmidtke. For this episode, I'll be joined shortly by my colleague, Bryan Woodworth, another member of the Networking Global Black Belt team here at Microsoft. And it's good to be back. We've been on hiatus for some time now, and looking forward to starting this series back up and sharing with you all sorts of goodness when it comes to networking in the Microsoft Cloud. But before we get started, we actually want to welcome all of our customers and partners, and maybe some folks that have viewed this show before or have seen one of the recordings on Channel 9, or if you're either new to Microsoft or a new partner or a new customer that is looking for some more information regarding how to connect or how to build networking solutions within the Microsoft Cloud. This is the place to be. All the material here is public information. We won't be discussing any sort of NDA type material or roadmap items here on this call or in this show. What we can do is work with your account teams if you are interested in hearing maybe some roadmap items or specific use cases that you have. We can escalate that and you'll be able to address those questions then. But for this purpose, this show is all public information. And as always, feel free to use the IM window for any of your questions. We have a number of our colleagues that will be manning those questions. We'll be able to cultivate them and then either answer them during a specific section or later on in the show when we have our Q&A section. Now, these sessions are recorded and they will be posted at the aka.ms link you see here on the slide, and it'll be part of our Channel 9 platform. So look forward to getting this up there, and feel free to share it with your colleagues or coworkers on specific topics, and you could even fast forward to specific sections of the show and share those links out to your constituents. So just a refresh on how this format really works. So since we're coming back from an extended hiatus, we're going to be running this show every 2 weeks, and we're going to have a couple of different agendas that are typically going to be held here. One is a partner focus session. So at times we'll have episodes that we'll go through any sort of networking or security topic for about 10 minutes or so, and then we're going to bring in one of our valued partners in the networking space for about 20 to 30 minutes to go through their particular solution, how it adds value to the Microsoft Cloud, and how it assists with the networking side of it as well. And then of course we always leave a little bit of buffer time for question and answer, just to make sure we relay all the relevant information over to you and get all your questions answered. The other part of it is a deep dive session. So that's what we're going to be going through today, where we'll go through some short introductions like we're doing right now, and then we'll go through a deep dive topic. So sometimes it's going to be delivered by one of our black belts themselves, like today, or it will be a special guest within the Microsoft family that will be able to deliver on a specific topic. And of course, again, the Q&A at the end to be able to make sure all your questions are answered on that particular topic. If you're looking for a particular set of topics or any sort of information that you'd like to see in a future show, feel free to email us at gbb/mna@microsoft.com. That's a distribution list that'll hit all the folks that author this show, so then that way we could make sure that we're making valuable content for the community here. And again, we will be posting these sessions on our Channel 9 platform for you to be able to share with your colleagues. So the agenda for today, we're going to go through some networking announcements from Ignite. God knows there's a lot of them this time, and we'll be able to kind of highlight some specific new features on some of existing services and also some net new services. So look for that, and then we'll go through some updates on our own team, where we've been going through some expansions lately, and we finally found some great candidates to be able to join our team, Brian Ashley and Jason Gmitmer. and we'll be able to introduce them and kind of showcase what the networking black belts are all about, and kind of where we're at in terms of the team to be able to support you guys in all your networking needs and dealing with Microsoft. And then we'll hand it over to Bryan Woodworth, who will deliver a deep dive session focused on multi-region hub and spoke. And it will be an extended whiteboard session. We'll go through some specifics on routing within Azure and how to properly design that. And then again, Q&A at the end, to bring your questions to the forefront and make sure everything's cleared up for you. So let's talk about Ignite. So Microsoft Ignite, for folks who are unaware, is our customer-facing conference. It happens around this time of year, usually the third week of September. This year it was in Orlando, Florida. For next year, I would highly recommend you going to ignite.microsoft.com and seeing how you can get some early registration in, so then that way you could attend next year. Typically, a lot of our product announcements and sessions that really educate you on what's going on with Microsoft all up, not just within Azure. So whether it's modern workplace like Office 365, Windows Client, of course Azure and the apps and infrastructure track, and then data AI is a huge portion of this show. So you could easily get lost within the Expo Hall with all the different partners that are involved. So overall, it's a fantastic show to kind of get the entire breadth of Microsoft and also the latest updates from all of the product teams, and that's going to provide value in your ability to achieve more. So that's what Microsoft Ignite's all about. And if we look at kind of the networking services in particular, we've got a number of them that are brand new and some that have had some updates across the board, but what we're really focused on is the ability to provide choices in connectivity, also provide protection in using public cloud services, and being able to actually use our scale, whether it's through our backbone network or our infrastructure that we built globally, to deliver those applications, and all at the same time being able to monitor them the way that you've been accustomed to monitoring those solutions on-prem, but being able to use it in more of a cloud fashion. So a couple of these features out here that you might be looking through the list on that might jump out at you are things like Azure Virtual WAN or DDoS protection, Azure Firewall, the Virtual Network TAP, front door, and all of these things really can go through in detail, but we're planning on actually taking a lot of these topics and incorporating them into future Microsoft Networking Academy shows. So again, feel free to reach out to us to give us some suggestions and maybe prioritize our efforts, and maybe we'll choose some different products and feature sets that have been announced at Ignite and go through in depth on what they all mean quicker than normal based on your feedback. So as you can see here, there's a little bit more detail onto a lot of the announcements that we made at Ignite, spanning all of these different categories, whether it's connectivity, application protection, the delivery, and also the monitoring. So again, we'll be able to go through these in depth in future shows, but if you wanted to get your fix now, you could actually review any number of these recorded sessions from our Ignite conference free of charge. So if you look at the link at the bottom of this slide, myignite.techcommunity.microsoft.com/videos, you'll be able to put in the codes that you see on the left-hand part of the screen, starting with BRK, which stands for breakout, and the corresponding number for the sessions that you would like to view. So you could take a look at any number of these sessions and be able to get in-depth summaries of all the new features and functionality right from our product teams. So the folks who actually help design and implement these solutions are the ones that attend Ignite and be able to explain what the value add is, and also cultivate feedback as well, because even though we build these solutions, sessions like Ignite are really important to us to be able to get your feedback to be able to make further product enhancements. So again, please feel free to go out to this site, really take a look at these different sessions, and to be able to get some in-depth information on each one of these topics. So we've got some new team members on the America's Networking GBB team, and GBB, for those who might not know, means Global Black Belt, which is an organization within Microsoft that really provides deep technical expertise on a particular topic. Some other solution areas, as we call them, are things like SAP on Azure, open source, containers, artificial intelligence, Internet of Things, gaming, blockchain, and the list goes on and on. Networking is part of that, so we've been busy in recruiting and bringing on board some new team members in the form of Jason and Bryan, and of course we have Jeremy and Bryan Woodworth, who have been around for a little while now, and then myself, Jamie Schmidtke, who focuses really on our networking partnerships, including Azure Virtual WAN partnerships, ExpressRoute partnerships, networking systems integrator partnerships, and what have you. Bryan, Jeremy, Jason, and Brian Ashley are technical specialists that focus on the deep technical expertise with everything that has to do with Azure networking. So feel free to reach out to any of us using our email addresses listed here, and we'll be able to answer your questions and also get engaged in further designs of your network architectures and how you interact with the Microsoft Cloud. So what I'd like to do now is hand it over to Bryan, who is a member of our Global Black Belt networking organization, and he will be able to go through a deep dive session regarding multi-region hub and spoke, and he'll be able to bring up his whiteboard and start really going in depth on how customers can design their virtual networks within Azure to be able to create a scalable and also secure environment to be able to use more of Azure services. So Bryan, I'm going to hand it over to you.
All right, so here's our basic diagram of hub and spoke. Obviously, we have two connection paths in from on-prem and then from the internet. In this case, we have ExpressRoute coming in, and we have VPN coming in, VPN being able to back up ExpressRoute. We also here have a path for standard internet traffic in. In this case, the straw man example is that this is an e-commerce footprint, and so we have an Azure public IP, which is essentially fronting two firewalls that is going to serve as a secure tier or eDMZ out to the internet. These firewalls will then inspect traffic at a variety of levels. Sorry guys, that's just going to happen. This happens to me during my regular workday. Folks come and ping me and ask questions. And then of course, the firewalls are then going to have a path to these spokes back here where the applications exist, where content is being served, and then the responses will come back out to the internet. So that's kind of our working model today. This particular lab is meant to represent, again, an e-commerce environment. There are many other ways you could use this. Spokes can solve a lot of problems for customers in terms of what was within a spoke. In my lab example, the spokes represent different phases of an application. So for example, it represents prod over here, pre-prod in the middle, and dev on this side. That's one use case of many. A lot of other people will use them as security zones, different containers, if you will. That's an overloaded term, but different walled gardens for business units or tenants, right? A spoke can represent a lot of different things. These boxes, by the way, do represent VNets in this diagram. So in my lab, this is spoke 1, spoke 2, spoke 3, and this is my hub.
Bryan, are you presenting something?
Should be. Do you guys see my desktop?
Yeah, we see it, Bryan.
Good,
okay.
Thanks. All right.
So maybe it's my fault.
No worries. Okay, so the first thing we want to do typically in this environment is make sure that we have a transitive relationship with on-prem. On-prem being designated by this building and this firewall here. The vast majority of on-prem situations do have an edge firewall, either in the on-prem WAN location or has been moved up in the Meet Me, which is what this circuit icon would represent in this case. If we were to expand this icon out, this would represent, our ExpressRoute footprint in the Meet Me location, where of course we have our two active routers. Just very quickly, so we review what's happening, that have direct fiber cross connects to a partner or service provider router. And then what's connected in on that side is a variety of different things. One of them, which could be a cage that's being run in the Meet Me, for example, like an Equinix Performance Hub, for example. And in that cage, the customer has their own edge footprint there, and in that footprint is the firewall device along with routers and IDS, IPS, that kind of thing. That's one out of multiple kinds of designs, but a very common one. But of course, we always know that this firewall here exists. Okay. So what's going to happen in a transitive relationship is first we're going to need to take some steps to make sure that route health injection flows end to end through this topology. When we form our VNet peering relationships here, bidirectionally by going into the hub, peering to the spoke, and then going into the spoke and peering to the hub, so we have, again, a bidirectional relationship. We can then take further steps. There, under the peering panel of the hub is this box called use, rather in this case, allow gateway transit, which I abbreviate as AGT. This will prepare our virtual network appliances, the Express Route Virtual Network Appliance or the Azure VPN Network Appliance, for injecting the routes that they learn, Express Route being a BGP player, VPN either being static or BGP, projecting or injecting the routes that they learn upwards into the spokes, or downwards as we see in this diagram if we put gravity to it. So here, in order to allow this VNet to accept those routes that are coming from beyond those gateways, we need to click another box called Use Remote Gateway. Now what this will do is it will, if there's any gateway that already exists in a gateway subnet in this spoke, that must be removed or yielded, because it's essentially going to bind to the gateway in the hub as its parent gateway. So we can only have one gateway here in this relationship, and typically it will live in the hub. Okay, so in my lab this has been done, except noticeably in my third spoke, which is my dev spoke. I have not decided to do use remote gateway, and we're going to see the outcome of that in BGP and kind of just get a feel of what happens when you don't always configure transit and the outcome of that. There are reasons and situations where you don't want transit. In this case, with my dev hub, because it is currently under a skunkworks kind of motion, I'm not wanting on-prem to see it, and I'm not wanting it to see on-prem. And so by stopping route health injection here, essentially with VNet peering, everything becomes local just within my hub and spoke topology, meaning spoke 3 will see the hub, and the hub will see spoke 3. Likewise, as we move through this iteratively, hub will see spoke 2 and vice versa, and then hub will see spoke 1 and vice versa. Another interesting important thing in this relationship is that spoke to spoke through this topology in this exact stamp with this intra-regional stamp, spokes do not natively see spokes to the hub. And that's by design, meaning spokes are supposed to be sequestered, isolated, and secure from each other. If we want spokes to collaborate in this design, we need to introduce some kind of path for them to do that. And there are two outcomes for this. One is a trusted motion, where I'm basically going to insert a route or inject a route from my on-prem location, could be on-prem, could be from within the Meet Me as I discussed, that will summarize the address spaces of these spokes and essentially cause hairpinning so that they can thus communicate in a trusted path. So let's put some address blocks in here to make this more real. So let's say that in this case, on-prem is 10.10.0.0.16. Okay, that's a big block that I'm sending in. That's arriving in via BGP into the Express Route Gateway and then being propagated, of course, into these spokes via transit. So the spokes will see that block. In my case, spoke 3 wouldn't because I haven't allowed transit for that, but spoke 1 and 2 would. Okay. Now, let's put some blocks here. This is going to be 10, I'm going to abbreviate, 10.1.20, 10.2.20, 10.3.20, and 10.4.20. Okay, so each of my VNets is a 20 in this case, and then I'm going to subdivide down into the subnet level into 24s as I shard out for different workloads. Okay, now as I mentioned, natively, 10.1 will see 10.2, and each spoke will see the hub and that flat relationship, but 10.2 won't see 10.3, so we don't have native transit or hairpinning in this motion. Now, if I inject an umbrella route or a summarized route up from on-prem through Express Route, I will draw traffic out down into the Meet Me and cause a hairpinning between spokes. And what I mean to say here is that, again, if we magnify what's happening in the Meet Me, remember we have these two physical routers that are in there. We call those the Microsoft Enterprise Edge routers or the MSEE routers. they're active. Within their routing information base and their BGP route tables, they do hold the individual VNet blocks of each VNet in this topology as long as transit is enabled. So in our example, we would expect to see 10.1 in the RIB of these devices, along with 10.2 and 10.3. 10.4 actually won't be there because use remote gateways was not selected, and that block is not being transitively sent because it is not bound to this front express route gateway. This backspoke VNet is not at this time. The moment I tick this box, it then binds itself to this gateway and has end-to-end route health injection. And then we would expect that block to show up. Okay, so remember, in the routing table of this MSE topology, these routes exist. You could almost think about this, thinking about it end-to-end from a full functional standpoint in terms of where hairpinning occur and where routes exist. I explain to my customers as a border, spine, leaf play, where the spine is actually your hub, because remember, there's active routing and intelligence going on here in the MSE tier that matters and will affect an outcome. So if we look at it as that three-layered cake, things start to make a lot more sense. So for example, let's say that I inject what's called quad 0, which is the default gateway route. We call this forced tunneling, right? So that any other traffic that isn't local to Azure, to the VNet or the VNet peering situation, will simply match this lowest common denominator route and go back home. Okay, so let me clean up my diagram here again so I can draw the outcome correctly. You guys are going to see a lot of me writing and deleting this, just how I present. Okay, so in comes our forced tunnel route from, in this case, let's say it's the meet me. When, let's say I want to ping from a virtual machine in here, which is in a 10.2 block, let's just say 10.2.1.10, over to here in a 10.3 block, 10.1.3.10. This virtual machine is going to walk its routing table, and it's going to see a BGP route for quad 0. That's going to be its most specific match at this time in its position for this destination. Even though it's a spoke and it feels adjacent, actually, because remember, this spoke 2 block will not be in the effective routing table of spoke 1 by default. So this route, this forced tunnel route, will capture that. It will draw the packet all the way through into the express route gateway, all the way down into the MSEE, where that border router, as I called it, the MSEE, does have a path and essentially an interface, a sub-interface for that block. And it knows that 10.1.3.0, and in fact the whole 10.1.3.20 block, because that's what my VNet is representing, lives back here in express route and is essentially owned by this express route virtual appliance. So it will hairpin. The packet will hairpin, come back into the VNet. This express route virtual network gateway is situated in the hub. The hub doesn't have a route to the spoke. It sees this block and will forward. And sometimes customers want that. Sometimes they want spokes to collaborate in an untrusted way, and they just want this default motion. What's nice about this is when you have packets transiting from a spoke to a hub through the express route gateway without a firewall or other network virtual appliance intervening in the path, there's zero spoke transit for this. So remember, VNet peering does transit, right? The cost is modest, but it is there, and it can be a baseline cost. So if you move in this motion, if you actually have a firewall down here to catch your traffic through this forced tunnel and then sanitize and then hairpin back in, all of this transit from spoke to hub is not metered because it's natively going out the express route gateway. So that's one motion that customers will use for hairpinning from spoke to spoke. It's essentially trusted from this piece, or they'll put a metal on-prem firewall or another virtual firewall in their, say, performance hub, and then they'll hairpin and they'll get their compliance that way, and back it comes. Okay, that's one outcome.
Brian, you said in that scenario there's no VNet charge?
That's right.
Or VNet peering charge, I should say?
That's correct. Right. What's interesting is when we have a transit situation, just to reiterate, this is important, when we have a virtual machine initiating an outbound connection that this express route virtual gateway owns, say that is, something that quad 0 would draw, like a forced tunnel, there is no transit cost for that motion because it's essentially kind of skipping the VNet peering metering relationship, which is paying attention actually to destinations in hubs and other spokes, meaning from a hub to a spoke and vice versa. Yeah, so that motion will not meter because it kind of skips over that, goes to the express route virtual network gateway and out. Now, if we want to move our DMZ up into the hub, which is increasingly popular for good reasons, then this motion changes, and let's go through that. And that's really the main focus of this topic. And thanks for enduring me through this conversation. I wanted to make sure I laid a foundation. Are there any other quick questions?
Hey, Brian, this is Rakesh. Quick question here.
Sure.
What happens if you VNet peer the spokes? right? The S1, S2, and S3. If you VNet peer that, how would that impact the routing from over the express route?
Interesting, great question. So if I were to form a backend, what we call like a backhaul, if I'm peering back here, let me use a different color because, hey, I can. I peer these, then, and this is part of my model, we'll hopefully come to see this later, then basically I am creating a higher priority link where if this is 10.2 and this is 10.3, the effective routing table of the spoke will now show this block as a real VNet peering block, which means it's native to Azure. This is a very high priority space in the routing table, and will be optimized such that this kind of traffic flow will now happen east-west between the spokes. I now have, of course, improved latency and potentially improved throughput depending upon what my workloads need, but VNet peering charges will incur. So this will meter. Again, it's modest, but it will meter. It's $40 a terabyte basically in zone 1 to move, because it's 2 cents to leave and 2 cents to enter. So, you know, going one way is 4 cents a gigabyte and going the other way is 4 cents a gigabyte. But if we collapse and do the math, it's $40 a terabyte. So some customers will want to force tunnel for a variety of reasons. One, they already have invested in a firewall tier and a security tier on-prem. They're locked into that because they paid for perpetual licensing and they want to get ROI out of their metal footprint, right? They're not ready to turn it off yet, fully understandable. Also, some people want to move their security edge up in the Meet Me location and you know, use a managed service offering there, and so they can push their security tier up here in that edge, and they have a firewall there that they want to bring. And some customers also realize, hey, if I do it this way and force tunnel, I don't incur VNet peering charges, and they're just really trying to economize on their spend, and so they're wanting this hairpin motion out and back in again.
Bryan, if the default behavior you said from the MSEE is going to come back, what if they don't want to be from MSEE, want to go all the way to the on-prem and come back?
Okay, if they wanted to go all the way on-prem and come back, they can, but they'll need to take additional steps. Of course, we're going to forward them the routes that will be in that border location, in that MSEE tier. For every block that I put in a VNet will essentially emerge as a CIDR block in a discrete route from our BGP edge to theirs. So that's essentially how you control what you see from us in Azure over the private peering to the customer, if you're the customer in this case. So if this is my VNet organization, whoops, let's change my blocks. These are all 20s, by the way. Okay, so 2 and 3 and 4. Then those are the blocks that my BGP router will see here. Let's say it's on-prem right here behind the firewall. And actually, let's pause and take a moment and take a look at that. Sorry, but the question was, let me answer the question and then we'll take a look at that, because I want to show off this new lab that I have and give some props out to my Equinix peers that have helped make this happen. So you would have to forward those blocks deeper into your core so that you could draw the hairpin down even further. That actually would be challenging because the MSEE, in fact, has those blocks already, and it would be difficult to steal them from the MSEE. That's your last whistle stop, because when the packet gets here to the MSEE, you would have to create a forwarding policy, have smaller, more specific blocks down here, and reflect those routes back in. It's not simple to do, because the MSEE, again, says I own 10.1, I own 10.2, I own 10.3, and I own 10.4. So what you would have to do would be, again, to take those routes, give them back, give them a higher metric, or make them more specific. So you would split this 10.1 into 10.1.1.0.24 and reflect that back in and say 10.1.1.24 is down here, I own it, so that when the MSEE gets the packet, it says, well, I'm 10.1, but gosh, there's a more specific block that's further down. It's going to go down into the core and hairpin and back in. So it can be done, but it's not simple and not elegant. It involves stealing blocks that the MSEE owns and reflecting them back. So it knows that it believes that there's a higher priority path for a route that essentially is within its VRF. It's a good question.
So Bryan, quick question.
Yeah.
So when you said then when traffic is flowing from S1 to S2 through forced tunneling, we don't incur peering charges, right?
That's
so
right.
Isn't there kind of a peering relationship between hub and spoke one? I mean, at that moment, will there be any charges?
What's interesting is that I'm not the expert on this, but the VNet peering metering model kicks in when it sees traffic going between two essentially local virtual machines. So the example here being a client in a spoke hitting a firewall. That kind of motion sets off a flag inside of our SDN stack that will meter in the VNet peering relationship. The ExpressRoute Virtual Network Gateway from a spoke or a virtual machine in the hub does not cause that meter to fire. That interface is special. And so when a virtual machine in a spoke sends its packet directly to the ExpressRoute Virtual Gateway, technically it doesn't do that. To be very technical, it's a DSR. This gateway is an in, and it's the fabric that takes the packet out. But that's beyond this discussion. If you just think of this as an actual symmetrical device, logically it tends to flow better. So when the packet leaves and lands on this gateway to egress out of the VNet, that escapes the VNet peering charge. Our API won't fire for that or whatever. The rule inside of our SDN stack that fires on metering, there's actually a metering part of the SDN stack. There's a whole piece in there to capture metering. It won't turn on.
Okay, thank you.
Yeah, you're welcome. Okay, so now let's take a look. Oh yeah. So let's just see what my on-prem looks like. I want to give a specific shout out to Lee Sharping, Brian Petit, and Josh Shortley, my three colleagues at Equinix that helped me put this lab together. It is the first joint Microsoft partner lab in this sales organization, and I just wanted to thank them for their time, especially Lee, who was very generous with his time to make this happen. Okay, so I'm logged into a essentially Windows-based jump box in the Cisco Performance Hub, which is their side of their lab here, and this is just sitting right behind a virtual Cisco router, which is my BGP endpoint on the Equinix side that's completing the circuit. So I'm going to load this guy up. Open this up, log in. Okay, let's take a look at the BGP table. So this is what it looks like from the other side of ExpressRoute, which is fun because we don't always often get to see this. So this is my hub in US West 2. This is my spoke. So in this case, my blocks were a little different than the academic example that I showed in the diagram. It's a little bit more nuanced. So here I'm actually subnetting on 20s such that this third octet is changing for each of my spoke VNets. So my hub is my 0 network. Spoke 1 is my 16 network. Spoke 2 is my 32 network. Now remember, I mentioned Spoke 3 was missing in action. That is because I have not enabled user remote gateways. So watch this. This will be fun. So here's my topology. Here is my Spoke 3. This is my dev spoke. And I've intentionally kept it off the grid because it's not ready for prime time yet. If I'm doing continuous development, the moment that I'm rolling my code in this and it becomes viable, you see we gateway transit is disabled, and that is because I have not ticked this user remote gateways box. Now, in continuous development, as I'm rolling code and promoting different legs or different sections of my network to represent production, then I might want to enable transit so that on-prem can start to use this or test against this or have it be more real. So watch this. If I click use remote gateways and save, this is actually pretty fast. So now it's going to bind itself to the ExpressRoute Virtual Network Gateway in the hub. Okay, let's go back and check out the peering relationship. It should show complete. Still hasn't matriculated yet. Remember I said we're going to be at the whim of the demo gods here. Now we want to make sure that allow gateway transit is ticked in the hub because it is bidirectional. So let's go check that. It's just standard troubleshooting. I'm going to go back to my hub. For every VNet that I peer with, those settings are unique, meaning that I can have allow gateway transit set to one of my spokes, but not the other. So let's confirm. It shows enabled now, so we should be fine. Yes. So allow gateway transit and allow forwarded traffic are there. Allow forwarded traffic just means allow on-prem traffic or traffic from beyond the express route gateway that's not native to Azure to flow. So that would be my on-prem block. Allow that to flow into the hub. And then likewise, I need to have that box ticked on the spoke to allow that non-native block, that off-prem block to flow from the hub to the spoke. So that's what that box means.
Bryan, this is two-way traffic, or is it only the traffic initiated from on-prem?
I don't understand the question. It would be for traffic initiated on-prem. Oh, I see what you're meaning. Mean allow to forward traffic out?
Yeah.
I've never known the answer to that. Let's see. It allows the peers forwarded traffic into your virtual network. So it peers inbound, not outbound. If we take that help, if we take that help bubble literally and read it word for word. So yes, it appears to be ingress, not egress.
Okay.
All right. Now let's go back to my lab and see if that block has shown up. So let's run that command again. And presto change, there it is. Isn't that cool? All right. So that's an example of enabling transit selectively and having that route pop up on-prem and not. And then here is my other region. So I have a 10.2 series for my West Central hub, and then my other spokes here, my 16 and my 32 and my 48. So that's my full topology. So let's go back and take a look at that. Time is flying. We need to start talking about firewalling here. Okay. So this is what I currently have in my lab right now. So what's happening, again, is that this is 10.1. Now let's get more like my real lab. So this is 10.1.16. I'll try to leave these blocks up. 10.1.32, 10.1.48. This is 10.2, basically 10.2.0. This is my 10.2.16, my 10.1.32. and my 10.1.48. Okay, now this is where things get interesting. And on-prem in this case is 192.168.10.24. Okay, so this route, that route, let's use colors, is coming up from on-prem. And because I have two VNets connected to my circuit, that route is being injected across both hubs. Via gateway transit, that route is now coming into all of my spokes. And we just turned it on for my dev for the purpose of explanation. So that route is landing all the way this way. Now, interesting. Remember how I said that spokes won't natively see each other unless I'm summarizing them or essentially hairpinning them through a firewall, meaning that I'm providing another UDR, user-defined route, a static route here in this table that says quad 0, go to your firewall. And then that firewall would allow for transit between spokes because you're summarizing. It's just a different way. Instead of summarizing with BGP on-prem, you're summarizing in a user-defined route, something that will umbrella or supernet over all of those spoke blocks, send that matching packet to the firewall, which is in the hub and locally adjacent to all spokes, sees spokes and would forward accordingly. And that is a very powerful motion. Okay.
And
so,
Bryan,
yep.
Just to be sure, right? So you mentioned a firewall, but it could be potentially any NVA with routing capabilities like a CSR, Cisco CSR, for example, right?
Precisely correct. That's right. Okay. You just need some kind of forwarding device in there, right? Could be a load balancer, right. A WAF even. Yeah, good point. Firewalls are the most popular. I do more firewalls than anything else, but by and large, yes, I've seen some other things where CSRs are in there. That's more of your SD-WAN play, but yep. Okay, so interesting. Now, what's important in this discussion is when I bring multi-spoken hub in via express route, each hub, each side, each region, this is US West 2, this is US Central, has no clue that the other side is an Azure topology because it's all BGP. And in some way that's beautiful because it's kind of like fungible and repeatable, and I can treat other regions in the same way from a routing policy and a security policy that I can treat other private data centers and other on-prem locations like headquarters and manufacturing sites, etc. It all just becomes a seamless part of my BGP mesh. So what will happen is, remember, all of these routes, these blocks that I've described, as we've just seen in that routing table down in my lab, are going to come that way down into the meet me location, and then, as depending on where your BGP edge is, down into on-prem. And then remember, the MSEE is your border. And that we have to remember, it's alive and kicking in a deep part of this architecture. So it's going to forward those blocks. And over here, let me use colors again. So if this is my green side, let's just use 10.2 as the example, my 10.2.0, make sure I get that in there. That block is leaving here, coming into the border router, and coming back in this other spine. And it's coming in as a route type BGP. So are these. My 16 network, my 32 network, and my 48 network are all coming in individual blocks to my border and being forwarded to my spine. Boop, boop, and then transitively into my leaf. So guess what? Where I normally had a relationship where my 10.1.16 network here had a sequestered, isolated motion for my 10.1.32 block, not so across regions. 10.1.16 simply sees my other spoke as a native BGP block. So I'm trusted out of the gate. Does everyone understand the difference? It just looks like a BGP block. This spoke has no idea that 10.2.1 is a spoke, a hub, a VNet, whatever. It doesn't know. It just thinks it's a BGP block that's in another on-prem data center. So customers might be expecting, hey, I'm going to have security across all my spokes, net. They're all sequestered from each other. Negative. The moment that you connect via express route, these come in as route type BGP and are implicitly trusted. Enter the firewall, right? That's why these firewalls become so critical. That's one reason why the Azure firewall became so critical. It's because in these big enterprise topologies, most of the time customers are treating these virtual networks, these spoke and hub virtual networks, as security zones, meaning what's in there inside the VNet is a low to medium security risk plays, and they're careful, they're smart. They organize workloads according to stripe and type, such that intra-VNet collaboration through subnets is meant to be loosely trusted or mostly trusted. They use network security groups to make sure that we have good up and down, side to side protection between subnets and tiers inside of the virtual network. And then they reserve these firewalls for collaboration motion across spokes or across zones, because those are quite sacred, right? That's a recommended architecture, and we've seen a lot of traction there. So again, erasing. Cool thing about this whiteboard is the faster you erase, the bigger the circle gets. I just figured that out the other day. I had a eureka moment, so I'm going fast here.
Hey, Brian, can I ask a clarifying question?
Please.
And this spoke-to-spoke routing in a multi-hub and spoke model will occur regardless of whether the two hub spokes are in the same region or in different regions, correct?
Precisely correct. Right. This design is neutral to location. The only difference, and it's a subtle but important difference, is the SKU type that your express route circuit is set at. So for a standard circuit, this topology can be had all within a single geo, meaning within all of North America or all of Europe, for example. So these regions can all connect and be fully meshed up, and in this case in North America, in any of our commercial North American regions and Canadian regions. If I elevate this SKU to premium, then this whole model becomes, spelling is hard, especially while I'm presenting. I'm thinking about like 6 things at once. So if I move to my premium SKU, this becomes a globally viable model. So this, again, could be US West 2, and this could be, APAC Hong Kong. And then this whole design plays out exactly as it does here on this, in this example. So it's cool. It's very interchangeable. Now, other different things happen with premium too, just very quickly to review. When you're on your standard SKU, your hub connectivity count is 10. When you're with premium, it approaches as you fatten your circuit 100. So it's a bit linear. It's not precisely linear, but it's close. So the bigger my circuit gets, the more hubs I can connect in, for a total of 100 over 10 gigabits per second. And Charlie is on the bridge. I won't pester. He was when I first called in. I do not know if this is changing as we move to Express Route Direct, when we actually have 100 gigabit per second connectivity. If premium will then allow more hubs in, maybe we'll have him on and talk about Express Route Direct and its capabilities, and save that for a future discussion. But we do now, of course, have Express Route Direct. It is in preview, and it's very exciting. It is an offering where you peer directly with Microsoft. The minimum requirement here at this point is a pair of 100 gigabit fibers, so that needs to be clarified. You can't have Express Route Direct using a 10 gig physical link. They do need to be 100 gigabit links, But on top of that, you can stack circuits and SKU sizes of, say, 10, 40, or even 100. But we'll get to that later, that exciting announcement. Okay, so
Hey, Bryan,
yes.
quick question. What if a region goes down? So as you mentioned, U.S. West and U.S. Central. If the U.S. West totally go down, how the routing is going to happen from hub and spoke to the other region?
Yeah, very interesting. In this model, I'm standing on one leg. I don't have path diversity. I would need my VPNs to back me up on that if that circuit were to go down. These VPNs themselves, in my model, do not also have a site-to-site connection. You could do that, so you had your own IPsec backhaul in case a circuit failed. That would work. But essentially, if a region failed in this topology, that whole BGP block, that whole BGP family would become unavailable from the standpoint of this region, and probably from the standpoint of on-prem as well, which is why we need to have VPN backup and or move to this model, which is a two-circuit model.
Two-circuit model, okay. All right.
Right, exactly. So that way, if this circuit were to fail, I can still see my other region this way. This is not the purpose of this discussion. We only have 20 minutes left, so I want to focus deeply on the firewall piece. But just know that customers, and we can have this as a later topic if you want, will essentially take the routes that Azure is sending them. So if this is a 10.1 side and this is a 10.2 side, because I'm butterflied here, both of those blocks are going to be sent down both of these circuits, right? 10.1, 10.2. And then what needs to be done is those blocks need to be backhauled at a higher metric. So 10.1 and 10.2 need to be sent across to each other, across their WAN link back here, like this. But we would want local preference on this side to be 300 in this model if I'm what we call hot, meaning both of these regions are active and alive and one's not a cold spare, and I want this side of the world to go to hit its closest circuit to get to Azure All Up, and this side, say West Coast, to hit its Azure on-ramp to get to Azure All Up. And I'm, again, assuming that both of these regions are hot. But this metric would be 100, such that if this side fails, this circuit fails, 10.1 and 10.2 vanish from this side, but they are still being sent down here. They're coming on this path through this circuit like this. How's it going? It's coming this way and this way. There. So 10.1 and 10.2 are still visible to this data center across the backhaul, and the path would go like this. It would take the long leg, it would hit this data center or this location, and then come into Azure that way. So in this way, I have path diversity, and I'm insulated against the failure of any one particular circuit. So that is a very, very popular model. We do a lot of those for good reason.
Thank you, Bryan.
You're welcome. Okay, so let's get down to this firewall piece and talk about trusted and untrusted and what happens here. And then hopefully I'll have some time for lab examples. This is really where the rubber meets the road. Okay, so first understand, let's first take the model, which is the most standard enterprise model, which is on-prem doesn't trust cloud, cloud doesn't trust on-prem, and region doesn't trust region, which I'm seeing for a lot of financial, I'm seeing for a lot of manufacturing, I'm seeing for a lot of medical, I'm seeing for a lot of financial services. Okay, so all of these industrial services, all of these enterprises are taking the very same approach, where again, these become security zones. Things that are inside of these VNets are organized because they have low to medium trust requirements, but then anything that falls outside of that security zone is a high business impact security motion. So I'm collaborating across business units, I'm collaborating across legs of an application that shouldn't be talking unless I can know what's going on. I'm talking across tenants. Some of these times this is actually multi-tenant, so it's a company of companies, and this represents one whole company they own and another company they own, and so these things are very isolated and they need to be monitored very carefully. That is the most common model. So in this case, I have to have trust and auditing. I mean, I have to have an untrusted relationship everywhere. So what I need to do is I make sure that I'm guiding all of the packets between both a spoke and another spoke through a firewall, and a spoke and on-prem through a firewall. And this firewall here is going to be set up to make sure that it brokers that conversation both, again, to on-prem and across express route to another region, which again, from this guy's perspective, is simply another data center, so it doesn't know any better. And then also from on-prem in, that this firewall is stopping a trusted motion end to end. So let's look at how that's done. Okay, it's done with user-defined routes. So again, let's draw and let's talk about the real moving pieces here. So I'm 192.168. Let's just ignore this other thing for a moment. 192.168.10.24. That's my on-prem. This is my 10.1.0. This is my 16. This is my 32. And this is my 48. Okay, and then let's bring in this one spoke. Let's light him up and talk about him, because he's important. Let's 10.2.16. Okay, so first, how do I make sure, let's example A, that spoke 1 is audited to the firewall on its journey to spoke 2. And I had mentioned that, right? I need to create a UDR that will summarize and guide that traffic into this load balancer, which is sitting as an internal load balancer, .10, for example, and servicing this firewall pair. So my UDR would look like, I can write it over here, okay? So in this case, the UDR would be the destination that I need to reach is going to be 10.1.32.0. The type is going to be virtual network appliance. And then the IP address of that is going to be that of the internal load balancer of the firewall, in this case 10.1.1.4. But that only accounts for traffic moving this way from this spoke here, and I need to account for the response. Routing is bidirectional, right? So I have to go over to spoke 2 and write another UDR, and that would look like this. My destination is 10.1.16.0. My type is virtual network appliance, and the IP address I'm going to send that to is 10.1.1.4. Now that's cool, because watch this. When this is an Azure standard load balancer here, it uses a rendezvous hash, which is savvy to an inverse binary motion. That's a very complicated way of saying that the rendezvous hash inside of the Azure load balancer uses an XOR function across the source bit stream and destination bit stream, which are both 5-tuple entities, to tease out inversion. That's the purpose of XOR. If you look up that operation as a logical function inside of a program, if you take two bit streams and you munge them together and you XOR them, you get a third variable, which is immune to which direction the bit stream is running. That means that when I send a packet, a SYN, for example, erasing again, I send a SYN in to this load balancer, watch what's going to happen. It's going to make a load balancing decision to the firewall, the next best firewall. That firewall will forward. Here comes the SYN ACK. Now it's easy to think, oh, the SYN ACK should go back to the firewall. If you want a NAT in the firewall, that's fine. Then that UDR situation I'm discussing is not necessary. The source address translation in the interface of the firewall negates the need for the response UDR here in the other spoke. But if I don't want NAT and I want the real client IP addresses to be shown, I need to send the response back to the load balancer. The SYN ACK will have the same, when I run the bit stream the other way, it's going to fall to the same bucket. The modulus is going to be the same. So I'm going to fall back to the same firewall, and the firewall will re-deliver it back to the original client. And it all just works beautifully. So this needs to be a standard load balancer, and it needs to be listening on HA ports, right? So star, so it can be a gateway hop, and it needs to be the destination of the UDR for this to work. Now notice here how this firewall has two interfaces, potentially a third for management, which isn't shown. One to service the public load balancer on the outside, one to service the internal load balancer on the inside. This is your minimal viable product. It's very crisp and effective and keeps complexity and chance for error down. If we start overloading this and putting different other internal load balancers to catch for different motions, we run into problems where we paint ourselves into corners where you effectively can only have one destination route for a spoke that represents that spoke from the standpoint of Azure, and then you're going to have to choose which internal load balancer is going to handle that traffic, and you find yourself caught in a trap where if I am going into this internal load balancer for a given destination, then the response is going to have to come back to that same one, and it can't come back to this one, it can't come back to this one because it's a different load balancer and the hash might be in a different state and it might not go back to the right box. So that's the easiest way I can describe it. There's actually some more detail there. So it's really smart just to have one internal load balancer that you use for both on-prem and back, north-south as I call it, and then from spoke to spoke and east-west. Now, sometimes this drives firewall people batty because they have one interface that's a trusted zone in and out, but in Azure, that one interface is flat and services all and has routes to everywhere potentially, and so it actually works beautifully. You don't need multiple interfaces because Azure is a flat layer 3 switch. On the public side, we typically will need to NAT because the IP address is coming in as 1234 from the internet. When this hits the firewall and the firewall forwards it to the back end target here, the source address is by default preserved, 1234. The response will come around the firewall and leave the Azure VNet directly because that's how Azure works. And this firewall, this will reach the client. The client gets the SYN ACK. The client will then ACK, the three-way handshake. The load balancer will once again deliver the ACK to the firewall. The firewall, who's the state broker, sees the SYN. It never saw the SYN ACK, didn't ever get it, went around, and it receives an ACK to the SYN, and it's right, the TCP state machine on that firewall will go, bam, reset, pow, you're done, because it never saw the SYN ACK. This is classic asymmetrical routing. So in order to stop this, we typically NAT in the firewall for public things. We cannot use the public load balancer as a hop in a routing table. If we could, we would solve this. Then we'd say, for the response, route back here, this is your gateway, and then the same reverse hash modulus to the same bucket would work. We don't yet have the ability in a routing table to say, hey, routing table, destination, internet, hop, the type, virtual network appliance, hop or IP would be 16.21.23.25. And this has to do with the fact that this instance level IP isn't an IP in the same way the virtual machine is. It's actually a NAT as a service. But still, if this ever arrives, then that works, and it comes back out here, comes back to the load balancer, and then symmetry is preserved. So what customers will either do is they'll NAT in the firewall and solve that, or if they don't want to NAT, they'll actually create another route table here, and then they'll have a static route that points to the spoke, another UDR that points to the spoke, and if this firewall fails over, this other firewall will come over and rewrite the UDR so that its interface is now on the response path. This only works with active-passive. If it's active-active all the way, you can't have multiple default gateways, so you have to NAT, essentially. That's the short story there. Okay,
hey, Bryan,
now,
regarding the internal routing spoke-to-spoke through the Azure standard load balancer that doesn't require you to NAT traffic to have routing symmetry with multi-firewall, multi-NIC, is that something you discovered? Is that something that's intentional? And is this something that's kind of manifesting itself as terms of a suggested approach in our documentation and with NVA partners?
I think all the above. It was not heavily printed. It was, I mean, the load balancing team designed the product to work that way. It was something that was, it wasn't an accident that that feature was built, but it wasn't widely disseminated that this was a potential outcome. But this is why black belts exist. This is our job, right? We find these Easter eggs, these killer features, and we find repeatable patterns that make sense, that help customers achieve the desired outcome, and then we evangelize them and solidify them and realize them. So that's what this discussion is all about. That's why I'm having this. This is me trying to make this more real and bringing what I see in the wild into sharper focus so that we can all start to think about better ways to build things, right? So to your point, there isn't, it's hard to instigate and create best practice inside the organization. It takes time and reapplication and rinsing and repeating to find out what makes sense across the vast majority of customers to say this is a recommended architecture. So you have to go around the mulberry bush enough. And it's awfully hard to spontaneously come up with that, right, unless you have time on the stick. But again, that's why our organization exists. Okay, let's talk about what happens now. So we've talked about how I do trusted motion from spoke to spoke. Let's talk about, in our remaining time, and gosh, this goes so fast I don't have a lot of time to show my lab, which is too bad. Let's talk about going spoke to on-prem. So the same would apply. I need to have a UDR that points my on-prem block to this internal load balancer. And so that UDR would look like this. Let's say my destination, I'll try to write more neatly, is 192.168.10.24. My type is essentially virtual appliance. The IP address is going to be that of my Azure Firewall internal load balancer. And that would make sure that traffic, which is destined to on-prem, 192.168, is going to come flow this way into my firewall through the load balancer, leave ExpressRoute, and go back here. Now, here comes the response. Here comes the SYNAC coming back. I'm going to have to catch it right here in the gateway subnet. I can't catch it up here because this gateway subnet is the first whistle stop into my VNet, and I need to get that packet back to that firewall pronto, and I can't have it going around. Because if I do have it going around and deliver it to some of the thing out here that then reflects it back, my EDMZ and my IDMZ is busted, right? My firewall has to be the first line of defense for auditing and compliance on everything. So this is where I put the UDR. And that UDR would look like this. Destination, the spoke, 10.1.32.0.24. Type, virtual appliance, IP address, 10.1.1.4. Now I have my bidirectional route flow. So my UDR here will catch it. It goes back to the firewall. The firewall is wholesome. It gets the SYNAC. It forwards the SYNAC back to the client. The SYN will come. The SYN will hit here, hit this firewall, and go back. Oh, yeah, what I meant to say is, let me redraw this. When the SYNAC comes back, it comes back to the load balancer. The load balancer will do the hash. It will fall back to the firewall. So that's that funnel. These load balancers in this way become funnels. Everything pours into them. Both traffic going this way and traffic going that way. So I draw that for customers a lot. Okay, now let's talk about what needs to happen to have an untrusted motion between this spoke and this spoke. Now we're really having fun. We have two sets of firewalls. Which one do I use? The answer lies within the fact that this, remember how I said the UDR has to be here in the gateway subnet to catch it so that that firewall can be the first line of defense? That is your answer. If I try to point the UDR for this whole data center, this whole region, my 10.2 side, over here to this, well, that's fine and dandy. This guy can take the SYN. This firewall will get it. He'll forward the SYN to this ExpressRoute gateway. It will traverse my BGP backbone. It will come into here, and then I'm going to have a route here to catch it, right? And that route's going to have to go to this firewall. And then where do I send my response to? How do I get this response back to this same firewall? You think I could write a UDR there? Could I say, UDR, hey, for this block, point to this interface? The answer is no. You can't do that. I can't have the target of a UDR be a BGP block. If I could, that would be amazing. What a Christmas wish that would be. I could start writing UDRs for BGP things back here and actually having static routes point to on-prem things and other appliances outside of the VNet. But Azure isn't capable of that right now. So there's no way for me to, in this spoke, fix up the UDR to say, go back to firewall hub 1, firewall A hub 1, because the destination IP of this, 10.1.1.4, appears to this side as a BGP route. The UDR won't tolerate it. Does that make sense? You can't point a spoke back to this firewall, this internal load balancer on a UDR. UDRs have to stay local within your VNet. So this is how this design has to work. You have to pick the local firewall. So what you have to pick the remote firewall, because the remote firewall is the only thing capable of handling the UDR response packet. So you don't at all set the UDR here. To make sure that you have an untrusted conversation between this spoke and this spoke, you set your UDR here, and that would look like this. Your destination is going to be 10.2.16.0.20. Your type is going to be virtual appliance. Your IP address will be that of the firewall in my other hub, which is 10.2.1.1.4, like that, 10.2.1.4, which is this guy. Now, this is fine. This just is going to send the packet to ExpressRoute. ExpressRoute is going to shoot it across the mesh. When it comes in, this firewall is going to gobble it up. It's going to go into this internal load balancer. Now my firewall's got it. Now I'm home free. Now I can write my UDR here, UDR, and the destination for this would be the response back to my other spoke, which is 10.1.16.0.20. My type is virtual appliance, and my IP address is going to be back to that same load balancer, 10.1.2.4. Now the response is going to map back to this load balancer. Do it in green. The response is going to map back to this load balancer, go back to this firewall, go back over ExpressRoute, and then finally make its way home. So the answer is, when you are using firewalls in pairs and you're wanting to make sure that these spokes are in a untrusted situation, you have to set the UDRs for your destinations in the gateway subnet and let the firewall on the other region handle the symmetrical conversation. And then that works. Just remember, in a double region model, don't use the local firewall for the other region. Use the local firewall for that region, and then allow the UDR in the gateway subnet and the other firewall to handle it on the other side. And then everything works. Now, what if I want trust between spokes? What I can do is just global VNet peer them. So in this model where I have these UDRs set up and I want to create a blessed conduit in the back, I can use global VNet peering. I can set up a trusted mesh between spokes, and then I have a trusted motion where all the others are untrusted. And if I want to create something like this, a just-in-time access, I can start creating a mesh for collaboration that's trusted, and then as need be, I break it down again. And then I'm back to my standard UDR. And in closing, I will say the reason this works is because when I do VNet peering, including global VNet peering, those blocks carry a heavier metric than BGP. So when an Azure virtual machine sees a competing block, that would be, in this case, this side sees 10.2.16.0 as a VNet peering block, and it also sees 10.2.16.0 as a BGP block, the VNet peering block is going to win. It's more stronger. It has a higher metric. Because there are different kinds of system routes in Azure that BGP can beat, but a VNet peering route is not one of them. And we'll have to discuss that at another time. So I'm willing to go about 4 minutes over. Are there any other? I'm sure there's lots of questions, but I have time for 1 or 2 questions, if you guys don't mind hanging out on the bridge. Any other questions here? Was this helpful? Do you feel that there was value in this?
Bryan, this is extremely helpful. So
Very helpful.
So much for spending time. This is great.
All right, great. Well, more to come. Happy Friday to everyone. Thanks again, and we'll see you at the next one.
Great.
Thanks ever so much.
Thanks, Bryan.
Great session.